All right, so if my terrible memory serves me correctly, which is always suspect, we were talking about accelerometers, and I believe we were talking about step response. Does that sound about right? Okay, so we should be able to wrap this up relatively quickly. So let me just revisit this really quick. So step response of an accelerometer. So I believe I mentioned in the last class meeting that typically speaking, we use underdamped systems for MEMS accelerometers where we are exciting them at a much lower frequency than their resonant frequency. So we're dealing with a situation where the quality factor is less than 0.5, right? So if we were to go and look at our transfer function here really quickly, h as a function of s. Let me find that equation. Here we go. Well, I'm going to do the one h as a function of omega. Sorry, I'm being slightly more scatterbrained than usual here. That would be negative omega squared plus j omega times omega naught over q plus omega naught squared. And when we're dealing with, hold on, sorry. I'm trying to make sense of this. Well, the long and short of this is that for the situation where Q is greater than 0.5, this denominator is actually going to have complex conjugates. Okay, so we're going to have a response, and I drew a picture of it in the last class meeting where we had ringing and all of that kind of stuff. I'm going to define a new term here, okay? So this is going to be omega d, and this omega d is what's known as the damped resonant frequency, okay? And this damped resonant frequency is going to be equal to omega naught, our mechanical resonant frequency, multiplied by the square root of 1 minus 1 over 2q squared. So if we were to substitute in this definition of omega d, we could get a new resonant frequency for our system that will, not a resonant frequency, a transfer function for our system that effectively explains why we have that sinusoidally, exponentially decaying sinusoid, okay? So the transfer function in this specific case, when we're working with a Q greater than 0.5, should look something like this, right? So it's going to be our displacement over our acceleration. That's just our basic definition. Is going to be 1 over omega naught squared times this guy. So 1 minus 1 over omega d times the exponential of negative omega naught times time over 2q. And that exponential function is then multiplied by a sinusoidal function that is omega naught over 2q times the sine of omega dt plus omega d times the cosine of omega dt. And let's see, I need to close that large bracket and then close that square brace like so. So this is the mathematical equation that describes essentially this waveform. So if we have our step function as our input signal, I think I did that in blue on Wednesday, Monday, so I'll do it the same way now. Right, this is our input signal. Then our output would look something like this, where we can see that this signal is oscillating with some frequency. That frequency is omega d, and then it has the envelope of an exponentially decaying function, which is given by this part of the signal right here. All right, so moving on, let's talk about mechanical noise explicitly in accelerometers. And we're going to approach this from a signal flow diagram perspective. So I mentioned earlier when we were talking about noise that in a mechanical system, noise is caused by atomic vibrations. Same thing is going to be here, okay? So we're going to have some amount of mechanical vibrations that is caused by thermal noise. And this is going to set the lower limit for the lowest possible acceleration that we might be able to measure. So looking at an accelerometer from a signal flow diagram perspective, we have our input signal of an acceleration is going to be fed into this first stage. So I'm going to say that this is stage A1, and this is the acceleration acting on our mass. And so the output of this first stage is then some force, okay? Well, we know that any damping in our system acts as a noise force generator from our last lecture. So I'm going to add a noise signal here. F sub n with a bar over it will be equal to the root of 4 kBt times our damping coefficient gamma. And then the output of this sum is going to go into a second gain stage. So this will be A2. And this second gain stage is our spring system, which is converting our force into a displacement. So this is going to have a transfer function of 1 over k. And then out here on the far right-hand side, we have the output of our system, which is our displacement, right? So just recapping things, the mass converts acceleration into a force that is then converted into a displacement by the spring, okay? So from this description, we can come up with an input referred noise acceleration spectral density, okay? So the input referred noise acceleration spectral density is going to be x sub n dot dot with a bar over it. And that is going to be simply our noise force divided by the gain of stage one, or the square root of 4 kBt gamma over m. And because I have, so let me go back on my notes really quickly to make sure. So gamma, our damping coefficient, if you recall trying to find it in my notes, is related to omega naught m and q. So let me just do this as an aside so that you'll know what the hell I'm talking about, right? So we defined our quality factor q as omega naught m over gamma. Okay. So if I substitute that relationship in for gamma, or rearrange it and substitute, I can write this noise force spectral density as the square root of 4 kBt times my resonant frequency divided by mass times quality factor. And so this is what's setting the lower limit of acceptable accelerations that we can measure, okay? So this is essentially the noise floor for our system that is dependent on the resonant frequency of the system as well as the quality factor of the system. Yes.
This is us moving the force from the first stage over to the input side.
Yeah.
We divide by that.
Yep. So because it's only that one stage, if I squared it and then did the square root, it's going to be the same thing. So that's why it looks ever so slightly different from what we did before. If we had something over here on the second stage, we'd have to do the square root and then, f squared over a1 squared, that whole thing. Yeah. So this relationship looks like we can lower our noise by raising our quality factor, right? So as Q gets larger and larger and larger, it looks like this noise acceleration is going to get smaller and smaller and smaller. However, Q is related to mass as well, right? So in order for us to raise our Q, we would have to raise our mass. And so we're going to get into a situation to essentially where we're going to have to make our system so large trying to lower the noise that it's no longer a MEMS-based device, essentially. Okay. All right. So I might add some better explanation for this stuff over the break. I'm just dealing with the notes that I have right now. I want to move on to capacitive sensing now, I believe. So this is the first of the types of sensing mechanisms that we're going to talk about in this class. Get these notes back so we can look at stuff. So we can define a capacitor essentially as two conductors capable of holding or storing opposite charges. Okay. So in a capacitor, if the distance and or relative position changes between the two conductors, as a result of an applied stimulus, the capacitance value of the system will change. And so this is the basis of capacitive sensing. So for the overwhelming majority of MEMS capacitive sensors will be implemented using a parallel plate capacitor system. Okay? So I'll draw a simple picture here. So let's say that we have a top plate like so. And this top plate is attached to a spring through some form. Right? And then I've got a bottom plate down here. Okay. And this bottom plate is fixed to the substrate. Okay. So I've got some overall area between my plates. Or excuse me, the plates have a particular amount of surface area that I'm going to call A, and there's going to be some distance between them, D, okay? Not going to get too far into the weeds with a derivation here, but the capacitance of a parallel plate capacitor like this is given by the relationship epsilon. And actually, let me write this out a little bit further. So I'm going to say it's epsilon R times epsilon naught times our cross-sectional area A divided by the distance between those plates. Okay. So let me just annotate this real quick so everybody's on board. So this is the plate area. This is the plate separation. Epsilon R is what's, actually, let me do that above, is what's known as the relative permittivity. And epsilon naught is the permittivity of free space. Bless you. Which is a constant, like a constant of the universe. So epsilon naught has a value of 8.854 times 10 to the minus 12 farads per meter. Let me see if I actually have that written down anywhere, if I'm just doing that from memory. Looks like I might actually just be doing that from memory. Google it, I believe I'm right. The only thing that might be wrong, actually, no, it's 10 to the minus 14 if I have farads per centimeter. So anyway. Okay. So if we look at this equation, there are three different possible ways that we could change the capacitance of a system, right? If we can somehow make the area of overlap between the plates change, so that would be the rightmost term in the numerator there, then our capacitance will change. If we can make the distance between the plates change, the capacitance will change. Or if we could make the relative permittivity of the medium between the plates change, that will also make the capacitance change, okay? 99% of the time, it's going to be the area or the distance, okay? It is possible to develop a system where you change the relativity of the medium between the plates, because that's what one chapter of my PhD thesis is on. So I know it can be done because I did it. It's not particularly useful, but it can be done, okay? So let's look at a system in a little bit more detail. So I'm going to draw a picture here, or I'm going to attempt to draw a picture here of a bulk micro-machined accelerometer. I'm going to start with a big box, and then we'll fill in some information. See if I can make that lines smaller. So let's say that this section down here that I have is one wafer, okay? And I've got my bulk substrate material, and then I've got this section right here where essentially I've grown some form of electrical insulator, so probably some type of oxide. I'm going to fill this in this gray color right here, and I'm just going to put a note here that this is an oxide. And I'm going to duplicate this up above for a second wafer. So I've got a three wafer sandwich kind of system here. So up here is yet another wafer. And then this whole thing right here is going to be an SOI wafer in the middle. Okay. Let me pattern my insulator on this part as well. So in an SOI wafer, we typically have a thin insulating layer. So I'm going to, I don't want that color for sure. And I'm going to form some type of suspension system here. So I'm going to have this drop down. Like so. So that, just to make sure people are catching what I'm throwing here, I've got a conductor here, which I'm going to call this terminal B. I've got a conductor here, which is going to be terminal A. I need to give this some structure down here as well. And then I might have deep reaction ion etched this part right here, leaving me with a proof mass that is suspended in place. Right. And this terminal down here will be part C. Okay. So as this mass here in the middle experiences an acceleration in the up or down direction, then what we're going to see is that this gap right here, which I'm going to call D1, is going to change. And this gap down here, which I'll call D2, is also going to change. Well, if I set this system up correctly, both of these distances might be equal to each other. Okay, so if I set it up to where both of the things are equal to each other, essentially I have a situation that I can simplify into something like this. So I've got an anchor point up here. I've got an anchor point down here. And then I've got a plate here that is connected to some type of mechanical suspension. And this plate is allowed to move in this direction so that this distance D is going to get larger as this plate moves down. And this other distance, also D, if we set it up to where these distances are equal, will get smaller as the plate goes down. So that overall, we would have an electrical system that looks something like this. So here's terminal B. We have a variable capacitor. So I'm going to call this CW1. And it will have a capacitance of epsilon R, epsilon naught A over D plus X, the amount that our middle plate has gone down. This will be connected in series to our second capacitor. So this is terminal C of our system. Here we have some second capacitance, CW2, where we'll have epsilon R, epsilon naught A over D minus X, like so. And then this middle node, which is node A, might be where we measure the output voltage of our system. Okay. So we essentially have some form of voltage divider network here. Okay, simple voltage divider, where we're using capacitances instead of resistances. Okay, so I want us to take a moment here and see if we can figure out what our output voltage would be, right? So let's say, just for the sake of it, that node C here was grounded out, and we applied some DC voltage at node B. Okay. So how many of you guys know how to do voltage division with capacitors? Anybody? Not even any of my electrical students. All right, let's sort this out real quick. This is going to be a brief tangent, but we're going to use it a whole hell of a lot throughout this class because so many things utilize capacitive sensing. I'm just going to jump to the last page of this as kind of an aside. So I know that all of my electrical engineering students are aware of AC analysis. Are any of my non-electrical students know how AC circuits work? Okay, Jesus. All right. Well, do you know what an impedance is? Okay, so so what's the impedance of a capacitor? So the 1 over j omega c familiar at all? Okay. Or in the S domain, the Laplace domain, 1 over SC, right? So if I have a capacitance, some capacitance C, then its impedance ZC is 1 over j omega c in the frequency domain or 1 over SC in the Laplace domain. Okay. So whenever I have capacitors connected in series, like the situation that I have, um, so let's just put a voltage here, or actually, let me do this one better. A phasor voltage here and ground here. So we're going to have this capacitance. So I'm going to say that this has an impedance of 1 over SC1. And this guy will have a capacitance of 1 over SC2, or an impedance of 1 over SC2. Okay. This is our output voltage phasor. Okay. So using these impedances, we could say that our output voltage in this situation, V out, is going to be our input voltage that we applied across the whole system, our phasor voltage V, and then we're going to have a ratio of impedances, just like we would have a ratio of resistances with a resistive voltage divider network. So this output voltage is the voltage drop across this capacitor C2 with respect to ground. So I'm going to have 1 over SC2 in the numerator. And then in the denominator, I'm going to have 1 over SC1 plus 1 over SC2. Okay. That is a result of using both Kirchhoff's voltage law around this loop as well as Ohm's law in the frequency domain. Okay. So are we all okay with this thus far? All right, so I have what I would call an abomination here because I have fractions in fractions and all of that kind of stuff. So I am incredibly lazy. So I'm going to get rid of as many of these fractions as possible. Okay. So what I might do is I might take this thing and if I multiplied first by S over S, which is just the number 1, that's going to get rid of all of the S's in this thing, right? So I have one less thing to worry about. Okay. So the next thing that I'm going to do, actually, let me take this to another step here, right? So this is going to give me V times 1 over C2 divided by 1 over C1 plus 1 over C2. Okay. Close this off. All right. So now I'm going to try to clear some of these fractions. So I'm going to work on the bottom first. So what I'm going to do is I'm going to multiply that term of 1 over C1 by C2 over C2. And I'm going to multiply that term 1 over C2 by C1 over C1, right? That's both just multiplying by a factor of 1. And what that does is it gives me a common denominator in my denominator so that I can just add those bottom parts together. Okay. So if I manipulate this a little bit, I'll have V with a bar over it as my phasor input voltage. Still going to have a 1 over C2 up here, but now I'm going to have C1 plus C2 over C1 times C2. Are we all okay with that? All right. So I'm dividing a fraction by another fraction, which is the same thing as taking my first fraction and multiplying it by the reciprocal of my fraction in the denominator. So this is going to come out to be V times 1 over C2 times C1 times C2 over C1 plus C2. And we can see that this C2 right here cancels this C2 right here, giving us the relationship that my output voltage V out is just my input voltage times the ratio of C1 over C1 plus C2. So all of this to say, probably unsurprisingly, voltage division for capacitors also works backwards, right? Meaning that it's the one on top over the sum of the series combination as opposed to the one on bottom like it would be for resistors or inductors. So we've got this relationship right here. And now I'm going to go back to the previous notes. And we're going to manipulate this thing, okay? So if I want to find the output voltage of this guy, we're going to start with the DC voltage that I've applied on top times the capacitance CW1. So I'm going to write that as simply epsilon times A over D plus X, where epsilon by itself is just epsilon R times epsilon naught lumped together to be a single term, the permittivity of the medium, okay? Divide this by epsilon times A over D plus X plus epsilon times A over D minus X, okay? And I'm going to manipulate this guy very similarly to how I manipulated the last one, right? So let's look at this really quickly, okay? So I have epsilon times A in the numerator of the numerator, and then I have epsilon times A of the numerator of the denominator. So all of these epsilons and A's are literally going to cancel each other out. Meaning that my output voltage now really only depends on the distance between the plates and the displacement that we experience due to our input acceleration. Okay. So we'd have our DC biasing voltage multiplied by 1 over D plus X divided by 1 over D plus X. I'm intentionally leaving a big gap here so I can play around with the algebra again. 1 over D minus X, like so. Okay. So what we'll do is we'll multiply this guy up here by D minus X over D minus X. We'll multiply this guy down here on the bottom left also by D minus X over D minus X. And we'll multiply this guy right here by D plus X over D plus X so that I have a common denominator in the numerator of my overall thing and a common denominator in the denominator of my overall thing so that all of those denominators cancel each other out, leaving me with my DC voltage times, I'm going to have a D minus X in my numerator. And then I'm going to have a D minus X plus a D plus X in my denominator. it should be pretty obvious that this minus X and this plus X cancel each other out, leaving me with my DC bias voltage times D minus X all over twice D as my output signal, right? So hopefully you all can see that, excuse me, a change in position of that plate will yield a specific voltage, right? So if we have a large change in position, we're going to translate into a large change in our output voltage. When X is equal to 0, this is just going to be half the DC voltage, right? As these plates move further apart, this is either going to get larger or smaller so that we can see whether or not the position changed. And the size of our voltage is related to that change in position. Okay? So this is capacitive sensing in a nutshell, right? We're taking a mechanical change in position and using this spring mass damper structure in order to generate an electrical signal at the output, which we can measure and use to quantify the amount of mechanical change that our system underwent. Okay. So let's come down here. Okay. So most capacitive measurements are based on observing a change in the current flowing through the system. Okay. So you might be thinking to yourself, and let me scroll up here just so we can maybe have it in the same picture. So I drew this schematic representation of our bulk micro-machined accelerometer, and we only played around with voltages, right? So this is essentially just voltage manipulation because we're doing voltage division, this, that, and the other, okay? And then I come here and I say, well, most capacitive measurements are based on observing a change in the current flowing through the system. And you might be saying, well, what the hell are you talking about? Everything we just did is in terms of voltages. Except that to a DC system, both of those capacitors actually look like open circuits. It's not until we perturb the system that we're actually going to see that impedance, which will cause current to flow. So it is really actually the current that's changing that we are actually quantifying with that. Okay. So the current flowing through a capacitor, I sub C, as a function of time. Let me ask my electrical engineering folks here. What's the equation for current through a capacitor in the time domain? The derivative one. It hurts my heart that it's taking you guys so damn long.
D or C D I.
Derivative of the voltage, right? So C times the derivative of the voltage with respect to time. That's what we dealt with in circuits 1, circuits 2, circuits 3, and all of that kind of good stuff, okay? But that's only actually half of the story, okay? Because we are making an assumption here that our capacitance isn't changing. But in a system where the capacitance does change, we're going to have a second term that's going to be V times the derivative of the capacitance as a function of time with respect to time as well, okay? So this part right here is what we were actually just exploiting, okay? So this is what you would get if you took the total derivative of C times V with respect to time. You're going to have a current due to constant capacitance and changing voltage, and then which is the conventional current that we're used to, and then we're going to have what's called the motional current that's due to the capacitance changing while we hold the voltage constant, okay? In normal operation, one term is going to be significantly larger than the other. So when we have measurement based on the change of voltage, this is a displacement measurement. Measurement based on the change in capacitance is a rate of change measurement. Anyway. So I'm just going to put a little underline here because we just talked about this. But this is what we're going to call our motional current in our system. Okay. So for a parallel plate geometry, we can write our motional current as some constant DC voltage times our change in capacitance with respect to time. Doing this as a partial derivative now. And I'm going to split that change in capacitance with respect to time up into two constituent parts. Okay. So, sorry, I could have VDC times the change in capacitance with respect to position multiplied by the change in position with respect to time. Well, the change in position with respect to time is just the velocity that our system is experiencing. So expanding this out a little bit further, we would have our DC voltage times epsilon times area. Let me explain where this next term is coming from really quickly. So let me just do this in blue as kind of a tangent thing. So we know that C is equal to epsilon A, let's say, over D minus X. Okay. The derivative of our capacitance with respect to position would be epsilon A times the derivative with respect to X of 1 over D minus X, which is just going to come out to be epsilon A over D minus X quantity squared if we use the reciprocal rule. Okay, so that's where this guy's coming from. So I'm going to have epsilon A over D minus X squared times the derivative of X with respect to time. And this will be approximately equal to our DC voltage times epsilon A over the distance between the plates squared times our velocity for D much, much greater than our displacement. Okay. So if our gap between the plates is much larger than the displacements that we are getting due to our change in acceleration and all of that kind of stuff, then what we get is a motional current that is proportional to the velocity of the capacitor plate. All right, let's work an example here. And this will probably be where we stop for the day. So I'm going to attempt to draw another shitty picture with you guys. So let's say that we have something like this, okay? So this is one silicon wafer that was etched to produce a very thin diaphragm here, like so. And then this silicon wafer is going to be mounted on top of another structure. So let me draw some stuff here. So we're going to have an insulation layer right here. So this will be SiO2. And then I'm going to draw a relatively complicated looking structure underneath here. I'm going to draw another one of these on the other side. Bear with me. So this is silicon. This is silicon. So this is 3 total wafers. And then I'm going to try to draw this part here, and I'll explain what the hell it's supposed to be in just a second. So this bit right here represents a fixed lower plate with holes in it, okay? And the reason why we want to have holes in it is because we don't want air resistance to prevent, essentially to push on the diaphragm as it moves. So air is free to pass through that fixed lower plate as that diaphragm deflects up and down, okay? So this terrible picture, I admit, is a MEMS microphone like we have in our phones. Okay. So from a circuits perspective, actually, won't even bother drawing the circuit. It's not useful here. So let's say, okay, so we have an area of our plate of 1,000 microns squared. The distance between our plates is 1 micron. We are going to have our frequency of oscillations, in this case, we're going to say is 500 hertz. Realistically, if we had human speech, it's going to be anywhere between 15 hertz and I think around 10 kilohertz. But let's say this is a person with a relatively deep voice talking in a monotone. Okay. So 500 hertz. And let's say that our displacement that we experience, so our diaphragm displacement is going to be 10 nanometers. And what I want us to figure out is the motional current through the capacitor if our DC bias voltage for this system is 5 volts. So before we get into this explicitly, right? So we've got an equation up here telling us what our emotional current would be. By the way, I would argue that 10 nanometers is significantly smaller than 1 micron, right? It's only 1% of that. So I think we can use this approximation. But in order to use this approximation, we need to be able to figure out what our velocity of our plate is. And we were told the plate's displacement as well as the frequency at which the plate is oscillating, okay? So I think, and feel free to correct me if I'm wrong here, I could say that our plate displacement as a function of time would be 10 times sine. The reason why I'm using sine here instead of cosine is because I have to take the derivative of this thing, and I think the derivative of sine is positive cosine. So I'm just trying to not to add an extra negative sign because I'm lazy and I don't want to deal with it. Okay. So 10 sine times our angular frequency, which is going to be 2 pi times our linear frequency. So 2 pi times 500 would look like 1,000 pi t nanometers. So before we move on from this, is everybody okay with this being our representation for our plate displacement here? Does how I got to this result make sense to you all? Cairo, you're shaking your head no. Okay, fair enough. So X right there represents our plate displacement, okay? So we have a displacement amplitude of 10 nanometers. We're told that it's vibrating at a frequency of 500 hertz. I am making an assumption here that we are having sinusoidal oscillations because I don't have any other reason for that. Okay. So if we have a sinusoidal oscillation, which has an amplitude of 10 nanometers and a frequency of 500 hertz, the only thing that doesn't really track is where this 1,000 comes from, 1,000 pi, but that's because it's 2 pi times the linear frequency gives us the angular frequency for our sinusoidal function. We all okay with that? All right. So let's take the derivative of this guy real quick. Which is just going to be x dot as a function of time when we throw that into our prior equation. So hopefully we all remember how to take the derivative of a sine function. So it's going to be a cosine function, but because we have an angular frequency here, that's going to get pulled out because of the chain rule. So we're going to have omega essentially times the amplitude of our signal times the cosine of omega t. And if I put numbers into this thing, right? So that would be 1,000 pi times 10 nanometers times cosine of 1,000 pi times time. I want to make a small change here. Sorry. 1,000 pi radians per second, being explicit with the units here. My apologies. Times 10 nanometers. Let me write that better. Times the cosine of 1,000 pi times time. So radians are a dimensionless quantity. So I'm just going to scratch that guy out. So we're left with nanometers per second. That seems like a reasonable thing for a velocity, since velocity is typically measured in meters per second, okay? So 1,000 pi times 10 to the minus 10. You're right, 10 to the minus 9. 10 times 10 to the minus 9, yeah. Is going to come out to be 1, 2, 3, 4, 5, 6. 31.416 times 10 to the minus 6. So this will be micrometers per second. All right. So from here, it's just straight plug and chug now, right? We know what our DC voltage is, so we can come over here and say our motional current is going to be, let's go back to our equation, our DC voltage, 5 volts, times epsilon. So our dielectric medium in this case would be either air or a vacuum. So we're just going to use epsilon naught because the relative permittivity of air is just 1. So 8.854 times 10 to the minus 12 farads per meter. Scroll up here again. Our area is 1,000 microns squared. The distance between our plates is 1 micron. So if we go up here, this is d squared. So we're going to have 1 micron squared. So luckily for us, this micron squared cancels that micron squared. And then lastly, we have our velocity, which we got to be 31.416 cosine 1,000 pi t micrometers. Per second. So let me just look at this really quickly here. So I'm going to throw a couple of more conversion factors on here at the end so we can sort some things out, right? So a farad is an amp second per volt, okay? So 1 amp second per volt is the same as 1 farad. Okay. So this gets us this farad cancels this farad. This second cancels this second. This volt cancels this per volt. Now, up here, I have micrometers in the numerator, and I have a meter in the denominator. So I'm just going to do a conversion factor to get rid of both of those guys, right? So that's going to look like, let's see, 10 to the 6 micrometers for every 1 meter. So this meter in the numerator cancels this meter in the denominator. This micrometer here in the numerator cancels this micrometer in the denominator. And all I'm left with is amps. Okay. So if I put this big ugly thing into my calculator really quickly. So let's do that. 5 times 8.854 times 10 to the minus 12 times 1,000 times 31.416 divided by 10 to the 6th, I wind up getting 1.3907. So 1.391 times 10 to the minus 12 cosine 1,000 pi t amperes, or 1.391 cosine 1,000 pi t pico amps. So that would be the current generated by this particular transducer if it underwent vibrations having a frequency of 500 hertz and an amplitude of 10 nanometers. Okay. So in order to generate more current out of this system, what would we need? Well, a higher frequency is going to give us a higher velocity, right? Or a larger vibrational amplitude, meaning that we might need a thinner diaphragm or something like that so that it can flex more easily, okay, in order to drive more current out of this thing. All right, we only have 2.5 minutes left of class, so this is as good of a stopping point as any. So we'll continue on our discussion for capacitive sensing on Friday. And honestly, it probably will go all the way through Friday, and we may still be talking about capacitive sensing when we get back from the holiday.